Solutions. Hold on, make sure I can write. Oh, I can. Good. All right. On to solutions here. So what is a solution? It is a homogeneous or homogeneous mixture. That means it's uniform throughout, like Kool-Aid, like any colored liquid, where you know you have two pure substances mixed together, something dissolved in the water being one pure substance. In the instance of Kool-Aid, that particular example, we're talking sugar and some flavoring powder mixed together, and then it turns into a nice colored liquid depending on your flavor. Like cherry would be red, or grape probably would be purple. But you can't tell the particles, but you know it has multiple substances, pure substances in there. Now, the first one that gets dissolved and it's in the lesser amount is going to be your solute. It is being dissolved. The solvent is the one present in greater amount, and for the instance of the Kool-Aid example, the water would be doing the dissolving, or does the dissolving. Okay? So you have your solute and your solvent. Okay? Solute, once again, the lesser amount, the one being dissolved, and the solvent is the one doing the dissolving and the one that has a greater amount. Any questions on that? Pretty simple. Easy concept. Two parts to a solution, and some solutions have multiple things dissolved in it, like Coke, for instance, has the water, but it also has sugar, it has caramel, it has carbonation, which would be carbon dioxide gas. So solutions can have lots of different solutes dissolved in them. Characteristics. When we say the word soluble, we're saying will dissolve in. And usually, when we use the word soluble, we're talking about a solid solute. Okay, there are little nuances to some of these terms. You remember your solubility rules, and you looked at the chart and you said this one was going to be soluble, this one would be insoluble. The one that said insoluble would tell you what the precipitate was going to form from the reaction. Well, same kind of difference here. We're looking at solid. If you put it in the water and it doesn't dissolve, it would be insoluble. If you, like salt, you put it in water, it does dissolve, it would be considered soluble. So we have our Kool-Aid, we add it to our water, and then it makes our nice Kool-Aid solution, the drink that everybody likes to have. But once again, it's uniform throughout, so it's going to be a solution. Anything that's uniform throughout doesn't have to have liquid involved. It can be in other phases. But if it's homogeneous or homogeneous, it's going to be considered also under the classification of solution. Now, miscible, it's kind of a different word, and I'm going to cross this out and change this. It says dissolve, but I like the word mixes with instead. So we're referring to, when we're saying something's miscible or immiscible, we're talking about two liquids. Are they mixing? Okay, or we're talking about two gases. Are they mixing? Miscible is more of a gas-liquid reference, whereas soluble, you're really talking about a solid dissolving in a liquid. So that's a little bit of a nuance in the way that these words are phrased. Okay, so miscible, really referring to like taking alcohol and putting it in water. They mix. Okay, and they would mix very easily. But something that wouldn't mix would be like oil and water, and we'd say that's immiscible. Okay? Pure substances. Remember, pure substances are only composed of one kind of atom or molecule. I went too far, sorry. So like in the box here, the only thing present is that two-atom molecule. You could call it sodium chloride as a compound. You could call it HCO. I mean, it could be a bunch of different things, but the thing is that there's only that substance. There are no other substances mixed with it. So pure substance composed only of one kind of atom or molecule or particle, I guess would be the best way to say that, or particle. So you can take a moment and you can write the definition around the boxes. or you can fill it in the top of the box and then do the drawing underneath. It doesn't really matter. You choose. All right, so next thing we'll be looking at is a solution, and really all you need to write, of course, is the first sentence right here. Uniform mixture of a solute and solvent, okay? The solute particles get surrounded by the solvent. So in this particular case, we're looking at this picture. Which one is going to be the solute? Which one is the solvent? Which one's the solvent, anybody? The red circles, how do I know that? Because it's in the greater amount, yes. So our blue-yellow molecule here, that would be considered the solute because it's in the lesser amount. Very, very good there. So on to suspensions. Suspension's a mixture that appears uniform while it's being stirred or mixed, but separates into different phases as the agitation stops, so the mixing or the stirring stops. So what you're going to see here is that they're larger particles, and like if you stir it, it looks uniform, but if you set it aside and let it settle, the larger particles fall to the bottom, and it forms a solid layer at the bottom, like muddy water. You stir muddy water, it looks like brown liquid, but if you set it aside, you'll end up with a clear liquid on top and the brown solid mud on the bottom. Okay, so suspension here, ones where they fall to the bottom. And last but not least, the colloid. The picture will come in just a second, but let's go over what a colloid is. Mixture of particles that are larger than the size of a molecule but smaller than can be seen by the naked eye. So these guys are kind of an in-between size. Suspensions have larger particles. Solutions have very small particles because they dissolve and fit between the solvent. Here, milk as an example has a bunch of different things that pretty much stay. They're larger particles, but they don't fall to the bottom. They kind of just stay in the liquid, and therefore is called a colloid. But that also makes milk look opaque. Looks like you can't see through it. It's not transparent because those larger particles are suspended throughout all the liquid. They stay and they don't fall to the bottom. Other examples, because they do not settle when the stirring stops. Smoke, okay, that's another example of a colloid. You can actually see the particles, but it's kind of staying in its big cloud unless wind comes along and takes it away. Fog is another example of a colloid. You see all of the particles out there. It's very dense. Okay, it can be really hard to see when you're driving sometimes, but the liquid in the gas there, okay, makes it really, really easy, especially to see the Tyndall effect, because everybody has their low beams on and it's scattering all the light of the car because we have all those other particles suspended in the air. Okay, so those are some examples of colloids. So they're kind of in the solution category, sort of not, just like suspensions are talked about here as well, although they don't stay dissolved. They just look sometimes like they're solutions. Okay, does everybody remember the Tyndall effect from the beginning of the year? Here is a nice, beautiful example of the Tyndall effect of a forest in the morning. Does anybody know why this happens in the morning, the Tyndall effects? The dew, yes, there's lots of transpiration from the plant leaves. And does everybody remember transpiration from last year? It's basically when the plant leaves are breathing, they're opening their cells. Some of the water escapes, okay, so it's like water evaporation from plant leaves, but it creates a lot of moisture in the air, and then that causes the scattering of the light. Any questions on that? So for our little drawing here, because they gave you the lovely little flashlight, although I don't particularly like these lines, I'll draw some in. So some things, like, of course, would get through, but if a light beam was going there, it would scatter, it would bounce off the particle, okay? Or get absorbed by the particle. Sometimes they do that too. Some of them go through, some of them scatter, okay? Like so. Some of them hit the particles, don't go through, okay? But that would be the generalized idea here. That large size of the particles of the colloids cause the light beam to scatter and become visible. So now we can actually see it. Whereas before, you know, can't really tell with the light. Okay? Any questions on that? Now let's go over some main examples of solutions and ones you might not necessarily think of as solutions. Like the first one is always a very prevalent question for the SOL. They love to ask about air. And they'll phrase it like this. Which of the following is a homogeneous mixture or a homogeneous mixture? Or it might say, which of the following is a solution? And of course, one of the choices is air. Air is actually a solution because the main part of it is nitrogen. 78% of air is nitrogen. So this would be your solvent, okay? Approximately, 19–20% is oxygen. So this is the main solute. However, that leaves, approximately 2% as the trace gases. And trace gases like argon, carbon dioxide, carbon monoxide, ozone, SO2, NO2, methane, there's lots of different gases that are in very trace amounts, but they exist in the atmosphere as well. So that is definitely a mixture. That is definitely a solution, a homogeneous mixture. I don't want you to miss that one on the SOL. It's very important. Okay, that one is frequently asked. That's why I'm making sure that you understand that air is a mixture. It's not just oxygen. When we breathe in through our lungs, yes, we're taking in nitrogen as well. The difference is the nitrogen doesn't diffuse into our bloodstream. We breathe it right back out. The oxygen diffuses into our bloodstream. Our body and our cells use that, produces carbon dioxide. So the carbon dioxide is breathed out with the excess nitrogen. Okay? Now, carbonated water. You know I love my seltzer water. Used to love my soda, but that's bad for you, so I'm going to stick with the carbonated water here. Carbon dioxide bubbles in here. Soda also has carbonation. This would be an example of where you have a gas, that's the solute, being dissolved in the water liquid that is the solvent. Okay? Another example of that, but this one is where the gas is the solute. There aren't a whole lot of examples like that where the gas is the solute. On to our next one, vinegar. Vinegar is a wonderful, the store-bought vinegar is actually only 5% vinegar, so it's a wonderful cleaning agent. But if it's only 5% acetic acid, remember the technical name of vinegar right here, technical name. If it's only 5% acetic acid, what's the other 95%? It's going to be water, yes, of course it is. So it's a very dilute solution, because most of it's water. There's just a tad bit of the acetic acid in there. Does anybody remember acetate? What's that polyatomic look like? Yay, I'm glad somebody remembers it. That's acetate, which is part of acetic acid. All we have to do is add on the H. We add on the H and it becomes acetic acid, which is better known as vinegar. Vinegar, they use that common name on the SOL as well as they use the formal name acetic acid, so you need to definitely know both of those. Now, vinegar is a good cleaning agent. Of course, we use it in lots of our food items, but the store-bought vinegar is only 5%. The very strong stuff that we buy from the chemical company to use for our labs, that's about 36% vinegar, a lot stronger. I can't even open it unless it's under the hood, because it's you think the fumes of just regular vinegar are kind of stinky. The stuff that comes out of the bottle, you have to turn on the hood because it's so potent that it could like singe your nasal passageway, your lungs. So it has a very, very, very strong smell compared to what just regular store-bought vinegar smells like. All right, next. This is another one that people frequently miss. And we need to make sure that you have the right strategy of being able to identify the alloys. Alloys are metal mixtures, okay? Metal mixtures. And the main one that you see up here is steel, where they take iron, and a lot of times with steel they put carbon in it, but they also can put other metals in it depending on the uses. They put and mix different metals together for stronger metals, sometimes more pliable metals, more malleable, more ductile. But alloys, mixtures of metals, are always going to be under the solution category. So a metal that you think of that you know by a common name like bronze. We all know bronze is made of metal, right? The best way to identify whether it's a solution or whether it's just an elemental metal is to look at the periodic table. Is bronze on the periodic table? No, it is not. If it's not on the periodic table, it's an alloy. It is a metal mixture. So be able to identify that. You can pull down the periodic table when you're taking your test or on the SOL and look at, make sure that if it's not a metal on there, it's an alloy. So it would fall under the solution category. Ocean water. I was just at the beach for spring break. It was fun. And yes, there was lots of sodium chloride dissolved in that water. And of course, that's a one that's highlighted a lot, talking about salt water. It's in our oceans. Basically, table salt just dissolved in there. Okay, so that would be a normal solid dissolving in liquid type solution. To acknowledge and know, and they talk about that a lot. Sodium chloride is a very common compound addressed in lots of different SOL questions. So, being able to identify solutions and given certain choices here, these are some really good examples, and they're frequently asked ones in the questions. Now, when we say that something is soluble, which we already kind of defined on the front, will dissolve in a solid, okay? And soluble, miscible kind of go together, but like I said, they're usually used, like soluble is used more when we're talking about solids, miscibles more when your solids are liquids or gases. Does it mix well? Okay. Yes, we'll come to the boxes where you can draw the comparison boxes in just a minute. But if it will dissolve, it is considered to be soluble. Now, there is a little bit of a difference when we're talking about soluble versus precipitate. Soluble is, will it dissolve? If I'm just taking the salt, could be any ionic compound, and I'm dumping it in water. If it dissolves, it's considered soluble. When we use the word precipitate, we're talking about we took two solutions with different substances in them, we mixed them together, and they reacted, they formed a new bond, and a solid fell out of solution and dropped to the bottom. So precipitate is really the result of a reaction. If you just take a solid and try to dissolve it in water, then you use the word soluble. And then, of course, insoluble if it doesn't dissolve in water. Kool-Aid, of course, is the main example there. Insoluble, a substance that does not dissolve in a solvent. And once again, we're kind of referencing liquid, solid going into liquid. Like sand is an example of that, where you'll just have the particles in there. Mud, and any of your insoluble ionic salts that are on your solubility rules would not also dissolve in the solvent. So we would call those insoluble. All right, for the last one. When a liquid solid will not dissolve in a liquid solvent or mix, like I said, I like mixes with better here. Okay, you get the prime example of like oil and water where it creates layers based off of density. Remember, the more dense one will be on the bottom, the less dense one will be on top. But that idea of forming layers, they're immiscible, they will not mix, like so. That is the key word here for this particular slide. But really, we're talking liquids and gases here. In the reference, the nuance is usually referring to liquid and gases when we're talking about the solutes here. Now for our lovely pictures for our boxes. So, the first box, here's another definition of miscible. Remember, it's referring to the mixing the two liquids or two gases. And here showing a lovely picture. Soluble. Basically, it's going to be uniform throughout. So it's like one solid color over here, like Kool-Aid. One solid uniform color. Insoluble, the particles, solid particles stay at the bottom like the sand. That was an example. Over here for the immiscible, we use the example of like the oil layered out over the water, like so. And we end up showing that particular diagram with the layers. So to understand and look at here next on the thing is why solvation, the process, the dissociation occurs. Well, the first thing that we need to know is looking at water here, which is the universal solvent that most things dissolve in, is a polar molecule. So by being a polar molecule, that means the electrons are evenly distributed around the molecule. If you remember, water here is a bent-shaped molecule. But the sides over here by the hydrogens, they're partially positive because the electrons don't spend as much time around there. The oxygen side is partially negative. And that's why we use the little delta symbol there to tell that it's a partial charge. Okay? So what we're going to be looking at now is how the solvation or dissociation process occurs. You see here we have plus minuses in the middle. That is the lattice structure of, say, sodium chloride. And the waters come around and surround them. Now I have a short video to show you real quick as to how this occurs. It's going to come up here soon, I think. Oh, here, it's over here.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Oops, hold on, I wanted to go back there so you can see. Yes, so this green one over here is a negatively charged anion. So the hydrogens, which are the white ones in the molecule, because they're partially positive, they are attracted to the chloride, so they face inward. The oxygen, which has the partial negative, not very attracted to the chloride, faces outward. Over here for the sodium, which is the positive one in the middle with the white, the oxygens, because they're partially negative, they're going to face inward on that one as they pull it apart, and they surround the sodium and the chloride and they break them apart, and then they have these water molecules all around them, kind of in a spherical sense. So let's go ahead and show you the picture of that. Here is the example of the sodium. As you can see, it's completely surrounded by water, but all of the ones facing inward are oxygens because of these partial negatives. They're attracted to that positive ion, the cation ion there, sodium. Okay? Now, the solid solute, so you can think of this as the crystalline lattice of the salt. You put that in the beaker of water. Of course, that creates the solution. And the solution is going to be the solute plus the solvent. And therefore, we have lovely pictorial representation. Now we're going to move on to our lovely 3 factors of what's going to affect solubility. The first one is the polarity. And if you remember, we talked about polarity in Unit 4. It was based on the symmetry of the molecule, whether it was polar or nonpolar. Now remember, polar stuff was like water, where it had an unequal distribution of the electrons, so you had partial charges. Nonpolar, of course, was a very symmetrical arrangement, so there wasn't one end that was partially charged. That is going to affect how things dissolved. Now, in your little paragraph above this chart on your notes sheet, this is what you need to find and underline. The statement where it says like dissolves like. So polar stuff that has partial charges like water can dissolve anything with a charge. It could be a partial charge or a full charge. Ionic compounds have full charges, so it has the ability to dissolve ionic compounds. It also has the ability to dissolve other polar substances. That's why alcohol can dissolve in water. That's why vinegar can dissolve in water. That's why a lot of things can dissolve in water. Water has that ability to dissolve the ionic stuff and the polar stuff because of the partial charge or the full charge. An example, of course, is the ocean water. That is definitely a polar-polar type arrangement. It's really an ionic compound, but those full charges allow them to break apart, as you saw in the video. The polar-nonpolar, no, they're not going to mix like oil and water. Instead, we're going to get the layers. They will not mix with each other. Also, another example of a nonpolar and polar one, the salt, which would dissolve in water, is not going to dissolve in gasoline. Does anybody remember gasoline is octane? Octane is a hydrocarbon. Okay? So gasoline is what? C8H18. So that's all symmetrical. Hydrocarbons of any kind, like your oils and fats and things, those are not going to, most of your organic stuff that do not have functional groups that are just hydrocarbons are going to be nonpolar. Nonpolar will dissolve other nonpolar though, so you could take the oil and stick it in the gasoline, it will mix. Like canola oil and olive oil will mix. So things that are both nonpolar, benzene's another solvent that's nonpolar that they use to dissolve other nonpolar substances. Now the solubility curve. Solubility curve shows how temperature affects solubility. On the graphs or the curves that you're going to see, on the X, there's always going to be temperature. On the Y, it's the solubility of the salt in a certain amount of water. In this case, out of 100 kilograms of water. Sometimes it's 100 grams of water, but it's telling you a certain amount in a certain amount of water. But most things, if you increase the temperature, you increase the solubility and it can dissolve more. There are a few ones that are different that actually decrease their solubility as temperature increases. There's a few. But for the majority of stuff, usually increasing temperature will increase solubility. Well, calcium hydroxide is one of them. That's lime. Most gases decrease their solubility with temperature as well. We'll talk about that example in a minute. One other thing we need to refer to is pressure, because pressure affects gas solubility. Gases exert pressure, liquids and solids do not. So if you put it under higher pressure, like most of your sodas and seltzer waters, of course, they're bottled under higher pressures to keep that gas trapped in the liquid. Okay? That's why it makes that sound when you open the can, right? Let's talk saturated, unsaturated, and supersaturation. So, unsaturated means I can add more solute. There isn't enough in there. I have not maxed out. You can keep adding. There is a less dissolved solute for a given temperature and pressure. I can keep adding in more. That's the whole thing for unsaturated. So, for instance, if you were making Kool-Aid and it called for, I don't know, a cup of sugar to make it taste right, to make it get to its right concentration. Even that, at a cup of sugar, you should still be able to add more. Of course, it would just taste very sweet and it would be, worse than Mountain Dew. But if you can keep adding more to it and it still dissolves, it's still in that unsaturated state. You can go ahead and leave the boxes open because we'll also be looking at those. Saturated is the certain point where you can't add any more. Okay? So if you continue to add more, like maybe when you were younger, you thought it'd be better to add more sugar to the Kool-Aid and you kept adding it. Or if you liked Tang like me, you kept adding the Tang. What would happen if you kept adding it? It would just fall to the bottom and you just have a nice little wasted sugar layer at the bottom, yes. Because it has maxed out. It has reached its saturation point. There is no more spaces for them to dissolve in, so it just falls to the bottom. So the saturated solution has the maximum amount allowed at that certain temperature and pressure. So you can't add any more in. Certain temperatures, like higher temperatures, usually you can add more than at lower temperatures, like I said, for most salts. But there is a given amount, and our solubility curves tell us that given amount. All right, so unsaturated versus saturated. Here in the picture, it's going to depict for you an unsaturated solution that has this blue-purple color. It's lighter too because it's not as concentrated for this example, so it's a lighter color. Over here, as you can see, the saturated one is very dark and you see little particles falling to the bottom because it can't absorb any more particles. It is now in the saturated. Can't take any more in. Falls to the bottom. Yes? As you see, the lighter color indicating, yeah, you can still add more. It's unsaturated. Darker color, particles at the bottom, can't add more. Now for the last one, which is the supersaturated. Supersaturated solutions, actually, they use them quite a lot in our commerce because most sodas and sweet tea and things are made from the supersaturation process. A solution that contains more dissolved solute than is saturated at the same temperature. How do they do this though? Won't it just fall to the bottom? You would think so. So what you have to do in order to make something supersaturated is like you'd increase the temperature so it could dissolve more, and then you let it slowly cool. You don't want to agitate it because then the crystals will start to fall out. But like I said, lots of the drinks are made, especially the super sweet ones, are made super saturated. So they heat them up and then let them cool down and then bottle them. But they have extra solute in there that typically wouldn't be dissolved at that temperature. Now on here it's showing you this little seed crystal right here. We call this a seed crystal. So if you have a super saturated solution and you drop a seed crystal in there, that could agitate and make it recrystallize. You could shake it too. You can do lots of ways to make the supersaturated solutions recrystallize. So over here it's showing you that this is recrystallizing into the solid. I also have a short video on this to show you real quick. It's very cool. Okay, so here in our little video we have a supersaturated solution. So watch what happens when he puts in the seed crystal. It creates a chain reaction of where extra solute now latches on and recrystallizes. So that one's a pretty good example of seeing that happen. Okay, so saw the recrystallization process is very fast, works really quickly with certain ones. Okay. Now, similar to the rates of chemical reactions, we also can increase and make things dissolve faster. So, how do we do this? There are 4 ways to do it. Particle size, stirring, temperature, and amount of solute. Okay? So, same idea as in chemical reactions. Particle size is about how the mixing occurs. Now we're just mixing, we're not actually reacting, so you don't have bonds breaking and bonds forming, but you're mixing the solvent and the solute together. So to get them to mix, okay, more surface area allows for more mixing, more collisions, for them to come in contact, so the dissolving process occurs faster. Okay, so that's really the sentence you want to concentrate on. As you increase the surface area, you make the particles smaller, they will mix faster. Okay, you'll get more collisions. It's like, for instance, a good example is in coffee or tea, if you put a sugar cube in there or just a teaspoon of sugar particles, the sugar cube is going to take longer to dissolve than the spoonful of sugar particles. They'll both take a while though, without any stirring. Of course, stirring makes that go a whole lot faster. So keep that in mind. Bigger particles, they have, just the outer parts of a bigger substance is going to be the one that's mixing with the solvent, so it's going to take longer. And we don't want to wait, that long usually when we're making solutions. All right. Let's look at mixing or stirring. Agitating makes them, of course, collide more. You mix them together. You're making the solvent and the solute collide more and mix with each other. So stirring, agitation, mixing, I don't care what you want to call it. Let's write that correctly. Stirring, okay. And with our flasks, a lot of times our bottles, we'll put the solid in there, add the water, and then we cap it, and then we can shake the bottle and make it dissolve a whole lot faster. Here goes the particles. There we go. Raising the temperature. Now this one is a little different in the explanation. You don't just have more collisions. Why do we have more collisions? Because an increase in temperature creates more average kinetic energy. What's kinetic energy again? Energy of motion. So if you increase the kinetic energy, you're making them move faster. If they're moving faster, they will mix faster, right? Don't forget the cute little delta triangle here showing you heat. The symbol we learned last unit for in chemical reactions. So raising the temperature increases the kinetic energy. That's important. And we end up increasing our rate of mixing or the solvation dissociation process. Now, of course, if you're making a very concentrated solution, it gets hard at the end there to get the rest of it to dissolve sometimes. Because if there's already a lot of solute in there dissolved, there aren't as many spaces to put the other stuff. So it takes a while. So if you already have solid in there, taking up space, when you add more, it's going to take longer to dissolve. So when I'm making super concentrated substances, I have to shake it a lot to hopefully get it to mix faster. And sometimes if I'm in a real pinch and I need it to go very fast, I might get out the hot plate and heat it up so it will go a little bit faster as well. Especially when you're making very high concentrated solutions. So as you can see, adding more solute, there isn't as much space for it, so it takes longer to dissolve. All right, moving on to our, one other thing about the factors here. It lists here temperature. The nature of the solute, like dissolves like, that's one of your factors. Pressure, of course, affects the gases. However, temperature, one thing to note about temperature, at higher temperature, gases usually are less soluble. Let's think about this. Prime example, 2 soda cans or soda bottles, it really doesn't matter, but one's been in the fridge, the other one's been sitting out on the countertop. I open both at the same time. Which one's going to go flat first? The one that's been sitting out all day on the countertop. Why? Because it's warmer. So what are the gas particles doing? They're moving faster. If they're moving faster, they can escape the liquid faster. And therefore, you have flat soda. So colder soda, of course, I think it tastes better, but it also helps to keep it from going flat as quickly. All right, so the ones that you're going to be seeing in your example are going to have solubility curves where it's typically out of 100 grams of water. Okay, so on our y-axis, you're going to see them out of 100 grams of water. In this case, we have grams of potassium iodide out of 100 grams of water. Of course, versus temperature. This is a solubility curve / graph. Yes, it doesn't look like much of a curve, but some of them actually curve quite a lot with temperature. You'll see on the other paper. So let's go ahead and identify the features of the graph. This line tells you what? What is that line telling you?
Saturated.
Saturated. This is the maximum amount that you can add at that temperature. That is your saturation. Okay? Now, if you're finding an area or identifying a point that is below the saturation line, like somewhere like there, or somewhere like here, what would you call the solution? This would be, yes, unsaturated. Okay, so if you're below the line, you can still add more. It's unsaturated. If I'm above the line somewhere, like over here, and I haven't added the seed crystal or agitated it, what territory am I in? Supersaturated now. Okay, where you could have more dissolved in there than it's supposed to be able to have if you agitate it or add the seed crystal. It will start to fall out of solution and go back to the line amount. Okay, so those are kind of what you need to look at when you're looking at the graph here. The other parts of the questions really are just, can you read the graph? There are a few ones where they try to trick you a little bit, but let's go ahead and look through some of these questions. The first one, at 25 degrees, about how many grams of potassium iodide will dissolve in 100 grams of water? So if I look here, this is what, about 30, so half of that's 25. I go up here, about how much? I mean, it's not exactly on the line, so we'll just call it like, 145, you think? 6, something like that, grams, okay. If you want to call it 150, that's fine with me, because it is approximately that much. About how many grams? We weren't going for exact, but needless to say. How about at 80? Here's 80, so we go up to the line. How much about that is that? About 190, I think that's a good number. Yeah, sure. Now on number 3, pay attention to the question and the way that it's worded. How many grams of potassium iodide will dissolve in 50 grams of water at 90 degrees? What's the problem there? Our graph is out of 100 grams of water. So it's really just a straight ratio. If you go over here to 90 degrees, which is about halfway between here, you go up, it's about what? 200 grams, right? So 200 grams of Ki over 100 grams of water. So if I need to know it out of 50 grams of water, then it's a straight ratio. So how many grams? 100. Very good. They could also ask you stuff like, if it was out of 200 grams of water, what would you do in that case? You would double it, and that would be 400 grams of Ki. Everybody get the idea there? All right. Number 1, under the saturation solution line, about how many grams of potassium iodide are needed to form a saturated solution. Now we're talking about saturation with 100 grams of water at 60. So if I'm at 60, where am I at here? How much is that about? Looks like, yes, right in the middle there, 175. So they could phrase it with saturation in the question. The last one on here, a solution of potassium iodide in water at 60 degrees contains 150 grams of Ki and 100 grams of water. How many additional grams of Ki must be added to the solution to make it saturated at 80? Well, if we're here at 60 degrees and we have 150 grams in there, right? At 80, we said about how much could be added? 190. If we've already added 150, but we want to make it saturated at 80, how much more should we add? Yes, you would take your 190, subtract that 150, 40 grams. Yes, 40 grams. Any questions? Yes.
May I use the rough stream?